What an FPGA vendor learns about IP. We're going to have some observations from a rather different point of view. And of course, I have to put in the usual disclaimers. Everything I say will be either my opinion or my misunderstanding. I do not officially represent Altera Corporation. And in case you've been reading the news lately, the acquisition of Altera by Intel has not yet been finalized, so nothing I say has anything whatsoever to do with Intel. The first obvious question is, why on earth should you care what an FPGA vendor thinks about IP? And I would argue that high-end FPGAs are actually a wonderful natural laboratory for intellectual property for a number of reasons. First of all, there's incredible churn. The leading FPGA vendors, Altera and Xilinx, tend to be early adopters of every new process node. And once in a while, somebody skips one, but in general, at the moment, for instance, Xilinx is beginning to ship 16 nanometer flip-flop, or FinFET devices from TSMC. We're in the process of completing a design with Intel on the 14 nanometer process. So, very much on the leading edge. Another aspect of that might not be obvious if you're not involved with FPGAs, when process nodes change, the microarchitecture of the FPGA changes as well. What that means from a designer's point of view is kind of as if when you went to a new process node, an evil demon went in and changed the architecture of your cell libraries. It's usually invisible to end users, but not always invisible. Also, there's a matter of span. Unlike anybody smaller than TSMC, an FPGA vendor typically sees thousands of designs in the course of a year, usually across hundreds of different application areas. And unlike the vast majority of SOCs, a lot of those designs won't be the canonical architecture of a CPU cluster, 2 or 3 levels of cache, and an industry standard bus. Some very unusual and very application-specific things happen in FPGAs. So we tend to see IP put together in ways that don't occur that frequently in the ASIC world. Another thing that makes the FPGA world kind of interesting for IP is just the fact that SRAM-based FPGAs are in-field programmable. So they tend to continue adapting to application changes, competitive pressures, and bad news from the applications engineering team, even after a product is shipped. So you can watch IP mutating after a product has gone out the door. All those things give us kind of an interesting perspective. Another thing that's rather unique about FPGAs is that where the rest of the world kind of recognizes 2 kinds of IP, soft and hard, we really have closer to 3. We have soft IP, pretty much like anybody else's. Supplied as RTL, goes through a tool chain, comes out not as a physical design, but as a mapping onto logic cells and onto interconnect segments in our programmable fabric. We have hard IP, skipping down to the bottom point there, which is like ASIC hard IP. It's either cell-based or it's custom, and it implements things that are like serial transceivers, high-speed serial transceivers, multiply accumulators, large memory blocks, and media access controllers, MACs. And in the middle, there's a thing that you could call firm IP or squishy IP. It's soft IP that has been pre-allocated to logic cells and then pre-routed. So it's not really a physical design because it's all about logic cells and routing segments, but it's ready to simply drop into place in the fabric. This is still fairly rare in the FPGA world for reasons that we'll get into in a few minutes. But 3 kinds of IP. And that means there's some interesting dynamics about what IP goes where. Sort of the reason for existence of the FPGA industry is that when a design team is facing unstable requirements. For instance, if there's an active standards committee working on function, or if the marketing department can get their fingers into it through the back door, IP tends to be done as soft IP and implemented in the programmable fabric so that you can keep up with the changes as they occur. And they do occur all through the design process, as I'm sure most of you are painfully aware. However, there's roughly a factor of 10 penalty in both area and power for implementing a function in the programmable fabric of an FPGA versus doing it as cell-based design and actually fabricating it into the FPGA. So stable things that are widely used and are interesting enough to present a design problem tend to migrate fairly quickly from soft IP to hard IP as soon as they start to become stable. So what you'd kind of expect is to see a life cycle for all IP where it starts out soft, goes through a period of refinement and regression to a stable state, and then becomes hard IP in the FPGA. One thing where you can see that happening right now is in Ethernet media access controllers. The high-speed Macs that go with the 28 gigabit per second transceivers are hard IP. They have to be. However, we're starting to see a lot of interest in MACsec, the secure media access controller. The good news is it's still in definition and it's still not widely used, so it's an ideal candidate for soft IP to be implemented in a programmable fabric. The bad news is it's enormous compared to an ordinary Mac, and so it takes up a significant portion of a small FPGA's resources. Now that sounds like a fairly reasonable and straightforward picture, but as always, things aren't reasonable and straightforward. I think all of you are painfully aware that as soon as you harden something, it turns out that the customer wanted something slightly different. Also, something that may not be as visible to IP vendors as it is to system vendors, integration usually turns out to be considerably more difficult than the customer anticipated or the IP vendor promised. Especially that's the case with a system that uses IP from multiple vendors designed at multiple times with different original target processes. Another thing that may not be entirely obvious is that as algorithms become more important to the industry, good mathematicians see an opportunity to make their careers on them, and algorithms sometimes get totally revised. One example right now is that in the last year or so, some very smart people have been working on the Reed-Solomon error correction algorithm. They've reduced the area required to implement it in hardware by about a factor of 3. So if you leave a block soft so that it can respond to changes like that, customers are going to complain about the area, power, and in some cases the performance. I'll put an asterisk on performance because comparing soft IP and hard IP performance is a much more complicated issue than it sounds like. If you harden the block, customers aren't going to like the behavior and they're not going to like the configuration. And if the algorithms suddenly change, you're kind of stuck. And all this happens, remember, in the context of continuous process migration. So the block that you may have had to do as a cell-based ASIC design a couple of years ago may actually be trivially simple to do in the programmable fabric now. One example is a thing that at Altera we call a triple-speed Ethernet Mac. It's a 110, 100 megabit per second media access controller. Used to be hard IP. For a couple of generations now, it's been so small if you put it in the programmable fabric that no one would even be able to find it. So we don't bother to do it as hard IP anymore. We just offer it as RTL. So with those pressures and those problems, what kind of a strategy do you take to managing the way you handle IP? There's a bunch of alternatives. One of them is to harden all of the problematic blocks and parameterize the heck out of them. Now in an FPGA we can do that because we have those little field programmable switches. So we can do a piece of cell-based logic, put switches around it that are essentially stated or control registers that manage the characteristics of it, and let the user figure out exactly how he wants it configured in a particular application. Another thing you can do, particularly since small real-time microcontrollers are so tiny these days and so fast, is shift a lot of functions into software, just stick them on an MCU core. And that has the huge advantage of letting your marketing department use the word virtualization. Another thing you can do is to try to overcome the integration issue by using kind of a Lego approach to architecture. One example of that is QSYS. There's a similar tool at Xilinx that's basically a graphic user interface that lets you assemble IP around a standard bus with virtually no logic design involved. There's also the AMBA AXI switch architecture that gives you a simple way at RT level of assembling IP. Or you could use a network on chip. And an option that's gotten a lot of publicity, but not a whole lot of traction in the last couple of years, I think, is that you can integrate a whole bunch of functions into subsystem IP and save your customer a lot of integration worries, a lot of problems about configuring and selecting IP cores by just giving them a big block that spans a whole area of functions. So there's a bunch of options there. Unfortunately, I try to always have bad news in foils. You can parameterize the heck out of hard IP, but it tends to become unmanageable. For instance, a modern high-speed serial transceiver block can have several hundred different parameters that need to be set by the user before it actually starts working. And it can become unverifiable because you now have 2 to the 100th possible configurations of this thing that really should be verified before you release the die. So big parameterized hard IP blocks tend to break down into separate, more specialized blocks just to manage the degree of complexity for providing documentation, for verification, things like that. You can take the software approach, but software has its own problems. If the software on the microcontroller doesn't meet its real-time deadlines, you have to create hardware accelerators. And now you've turned what was a fairly straightforward logic problem into a problem of designing an accelerator with very tight time constraints. So you may have made things worse instead of better. I think there was a mention a little while ago about that exact thing happening with cryptography. Yeah, easy to move public key encryption onto a microcontroller if you've got all day, but then you end up having to provide a very, very difficult to design, really, IP core to make it work on a reasonable deadline. Honestly, the Lego approach, no matter how you do it, costs you quality of results. One of the reasons for that is the curious fact that the FPGA backend tools, the mapping, placing, routing tools, do better if you give them a huge flat design than if you give them a hierarchical design that's broken up into nice, logical, understandable pieces. Network on chips are kind of a special case of that for FPGAs because they introduce their own requirements for some very latency critical IP blocks. And for FPGAs, that's a much bigger deal than it is for a cell-based ASIC. If you're going to have to put something like a switch block into the programmable fabric, you're going to have to be very careful about it. And so you may not be simplifying your problem with a knot. And finally, IP subsystems. There's speculation that we're getting increasingly interested in, that IP subsystems are actually mythological beasts. What happens apparently, is you can implement them, you put them out in the field, and as soon as you take your finger off of them, they begin to metamorphose into reference designs. And so instead of an encapsulated piece of IP that no one has to worry about anymore, you end up with all of the complexity of the individual IP blocks back again, plus software. I think this is still an open question, but it's something that we're paying careful attention to. Then there's another issue in the FPGA industry. For the big high-end FPGAs, most of the applications have been in a very few areas. The military uses them for things like radar and sonar signal processing. The communications industry uses them for things like packet switching. The wireless industry uses them in base stations and remote radio heads. All of those people either have FPGA company applications engineers on site, or they have very skilled FPGA design teams internally. But in the future, the growth opportunity for FPGAs is not necessarily in those areas, at least not until 2020 when people actually start deploying 5G cellular. It's in new areas. And as a generalization, the users in those new areas are mostly software-oriented people. They're not hardware designers. And they don't think of a design in terms of blocks of RTL and an industry standard bus. They tend to think more in terms of a computer program that makes lots and lots of function calls to application-specific libraries. And another thing that you find very quickly in dealing with people in this world, they think if something's important, it's open source, which does have influence on things like who pays for support and on revenue models. So the question that an FPGA vendor looks at today is kind of, now what? If big hard blocks aren't going to solve the problem, and subsystem IP isn't going to bail us out, there is one promising area, and actually it's something the FPGA industry has already been doing, and it's closely related to an emerging trend in the high-performance computing area. For want of an agreed-upon term, I called it domain-specific subsystem generators, which I refuse to turn into an acronym. If you have a tool that generates a piece of hardware for a specific application area, there's a bunch of good things you can do. One is you can have the input to the tool in the natural language of the people who are trying to use it. If what you're trying to generate is signal processing blocks, you can have the input in something that talks about signal processing, for instance. If you're trying to do blocks for geothermal exploration, you can have an application-specific language that's used by geologists, that kind of thing. Another point about subsystem generators is that they aren't necessarily synthesis tools in that they can generate software, they can generate soft blocks to go into the programmable fabric of your FPGA. They can also infer the use of hard IP that's already in the FPGA, like those DSP blocks or those big block RAMs. So they can put together a system out of 3 different kinds of components: software running on an embedded processor, soft IP, and hard IP. And as I mentioned, domain-specific languages and domain-specific libraries are increasingly being used in the high-performance computing world, probably because most of the people who are really good at Fortran are retiring. And people who are much more familiar with the scientific problem they're solving than they are with C programming took one look at C and said, why would I want to program a PDP-11? So they went off and did their own language. And I also said that the FPGA industry has already been moving in this direction. DSP Builder, for instance, an Altera tool, but there's a similar tool as Xilinx, takes Simulink models of DSP pipelines, directly converts them into a design that combines the hard DSP blocks in the FPGA with soft logic to link the pipeline stages together. OpenCL, which you may or may not be familiar with, is a language that started out at Apple and AMD as a way of doing parallel programming on heterogeneous multi-core systems that would hopefully be portable across different kinds of systems. What OpenCL does is to make you rewrite your C program in a language that kind of looks like C. And then it breaks it into two pieces. A piece of code that runs on a host processor and a group of things called kernels that you can then implement on a GPU or as soft hardware in an FPGA. And there's C-driven synthesis as well. It probably will not achieve the promise that it seemed to have a few years ago. But starting out with a C program and directly converting it to RTL and feeding it into an FPGA toolchain does in fact produce some useful structures in a bunch of cases. One of them is numerical pipelines. If you've got computations that don't have to be highly optimized and aren't terribly concerned about the energy consumption, you just need it to work, and you don't want to spend a lot of the design team's effort on it. So rather than making this informative, I decided to end it with a question. If the thing that seems to solve the FPGA industry's problems is a set of domain-specific subsystem generators, does that mean that we're going to see the emergence of a new level of abstraction in IP, along with hard IP that's tied to the implementation and soft IP that's tied to the structure? Are we going to start seeing executable models tied to the algorithm that can be fed into these domain-specific generators to produce the design? And are those going to become a distributable, licensable, and supportable kind of IP? I don't know, but for the FPGA industry, I have my suspicions, and we may be seeing something that's going to spread elsewhere. Thank you very much.